All right, here we go, part 2. We have the total heat capacity. Notice the units. What are the units on that? Kilojoules per degree Celsius, right? Notice it takes mass out of it. It was joules per gram degree Celsius. Now we're in kilojoules per degree Celsius. Because when you have a calorimeter, it's not going to change. The mass of it's not going to change. The amount of water you put in is not going to change. And so they just figure in a calorimeter constant. They just figure in the overall heat capacity. How much does it take to raise the whole thing 1 degree? And it's this many kilojoules to raise the water, the calorimeter, everything 1 degree. So the only thing that's different is we take mass out. So now you can just go to get kilojoules per degree Celsius. To get kilojoules, what's the only thing we have to do? Multiply by temperature. And that gets rid of degrees Celsius, leaves us kilojoules. So, okay, the temperature of the calorimeter increases from 23 to 30.5. What is the heat of combustion per gram? Per gram. So, I start with delta H of the reaction. It's going to equal. This is a calorimeter, but it's going to equal the negative times the 7.854 kilojoules per degree Celsius times my change in temperature, 30.57. Why did I raise it up? 30.57 degrees minus 23.44 degrees. And that turns out to equal 7.13. Is that right?
Yeah, 7.13.
So that's my delta T. So I multiply that out, so my delta H of the reaction overall is equal to negative 7.854 times 7.13 equals 56. I know, 3 sig figs though.
56.0.
Negative 56.0 kilojoules is the total amount of heat that was released. But when how much burned? We want it per gram of quinone. Well, we have 2.20 grams of quinone. So to get per gram, you just take kilojoules divided by the total grams, which is 2.200 grams. And that turns out to equal negative 25.5 kilojoules per gram. So here we're doing kilojoules per mole. This one in kilojoules per gram. Now, how do we do it per mole? Well, we can just say negative 20. We can do it 2 ways. We can convert the 2.2 grams moles and divide it in, or we can say kilojoules per 1 gram times the molar mass. 72 plus 4 is 76 plus 32 is 108. It should be 0.5, that's 0.6, oh, it's 0.1, 0.10. Over 1 mole is equal to 2,750 kilojoules per mole. Okay? That's a lot. Good source of energy right there. A lot of energy released when it burns. Okay? So the whole key is that you divide it kilojoules per gram, kilojoules per mole. Now, it would have been the exact same thing if you went 2.2 divided by 108.1, got an answer, and then divided that into the negative 56. You get the exact same, and you're doing the exact same thing. Okay? But you would have to use the negative 56, don't use the 25.5. If you divide this one by moles, then you're not gonna get the right answer. This is kilojoules per either 2.2 grams or however many moles this is. But either way. All right, last one in the book. 58. This is going to be an identical problem, okay? So I'm only going to erase certain parts. So we're going to do everything the same. This time, the heat capacity of the calorimeter is 11.66 kilojoules per degree Celsius. The temperature of the calorimeter increased. So if the temperature increases, is it endo or exothermic? Exo. So it's 26.37 degrees minus 21.36 degrees. So that's going to end up equaling, we want per gram and per mole again, and we'll come back and write the balanced equation. That's not what we're really looking at here. But what do we get for this value?
58.4.
Negative 58.4 kilojoules. But that's per how much? 1.800 grams. So we divide this by 1.800 grams, and we can get kilojoules per gram. 32.5 negative kilojoules per gram. And then we can take that, negative 32.5 kilojoules, multiply it by the molar mass of phenol. 72 plus 6 makes 78, plus 16 makes 94, 94.12. See, it is possible to add and subtract numbers in your head without a calculator. Just saying. I'm old, the bread's beginning to mold, but I can still add those basic numbers together. All right, so then we end up getting what?
Negative 3.05 times 10 to the third.
Oh, so times 10 to the third, so 3,050 kilojoules. All right, so these two problems are exactly the same, but what I really want to point out in this is the whole idea of heat capacity of the calorimeter. It just takes mass out. So you just have to go, again, the unit's kilojoules per degree Celsius. We just have to multiply by degrees Celsius to get to kilojoules. Use units. Units are your friends. Unit help you decide what you need to do, how you multiply. Make your units work out. Any questions at all on these? All right. Unfortunately, we're going to run out of time and not be able to go over all of the book problems. May have to do a third file in the 7th period today to do those. We can get one in.
I feel like we've had that 2016 question like 3
I
times. For some of the parts I just looked back and like,
I know, it is.
The
It's
one
like,
with the
well,
yeah.
we have, and it's because of different concepts are asked in that problem, and that's the whole thing on AP, is that it's not just a thermochemistry problem. It's not just a solutions problem. They mix concepts, which is one of the reasons why it's one of the more challenging AP tests, because you have to be able to synthesize the concepts together. So if we look at this one, okay? This is almost identical to those book problems that we just did. Yeah, right there. Yeah. So, this first one, A, determine the change in temperature of the solution. Well, this is just reading a graph. But delta T is always equal to what? T final minus T initial. So we don't want to just say that it's going to be 3.2 degrees. It's going to be 21.8 minus the 25.0, so it's going to equal negative 3.2 degrees. Okay? It's always T final minus T initial. Now, question B says, according to the data, is the dissolution of urea an endo or exothermic? So since the temperature is going down, what does that mean, endo or exo? Endothermic. The solution's getting cold, so it's endothermic. The temperature, change in temperature is negative. So when I put that into negative MC delta T, the negative and the negative are going to make it a positive delta H. But if it gets cold, the temperature goes down, it's endothermic. Temperature goes up, it's exothermic. It's that simple. Okay? So part C says, assume that the specific heat capacity is 4.2. Calculate the heat of the dissolution of the urea in joules, and then calculate the molar enthalpy in kilojoules per mole. Here's the exact same thing that we just did. So we have our delta H of the reaction. Delta is equal to the mass of the solution. The student places 91.95 grams of water in coffee and immerses a thermometer. After 50 seconds, the student adds 5.13 grams. So what's the mass of my solution? It's the combination of both, right?
Oh yeah, 97.8.
Okay? And then times, I'm gonna just block this out for right now, so we don't need that. Okay? Times, it tells me that the specific heat is 4.2 joules per gram degrees Celsius, times my change in temperature, negative 3.2 degrees Celsius. So all of that turns out to equal to 2 sig figs.
1300 joules.
13, okay, and this is negative here, so it's positive 1300 joules. But that's per how much? So that's the answer to the first part. Okay, that's B1. B2, we need kilojoules per mole. Okay, so I know that it's going to equal 1.3 kilojoules per how much? 5.13 grams of what's the compound? Urea, which tell me the formula. H2NCONH2. H2. Okay? So, how do I get to per mole? Just use the molar mass. So it's going to be times the molar mass, and what did you guys get for the molar mass of it? 60.6 or 06? 60.6? 06 actually, but so this number turns out to equal 15. Notice that when it reacts and dissolves as 15, when the quinone burned, it gave off 2,600 kilojoules or whatever. So the different reactions as far as getting the different heats of reaction. All right, you didn't have to do. No, that's just, was that? No, that's that. This is actually C1 and 2, isn't it? B was just whether it was endothermic or exothermic. All right, so I will either do the rest of this during 7th period on video, or Lauren and I could have a little quality time going over all the problems for the video's sake, just so I can get it up earlier. All right. There will be a part 3.